Practically all of modern physics relies on one principle, the principle of stationary action. But what is it, and why is it so important?
Say I threw a ball in the air and caught it within a certain time frame. This parabola is the path the ball followed over time, but let's imagine infinitely many paths this ball could have taken given the same time frame, initial and final positions.
Why would the ball follow this specific path?
The reasoning lies in the principle of stationary action, which states that the true path is that in which the action is stationary. To break this down, let's analyze how we are describing motion. We can use the Lagrangian, a function of generalized coordinates and velocity, often represented as the difference between kinetic and potential energy, illustrating a trade-off between the energies that describes a system's state locally. Therefore, if we integrate the Lagrangian to see how it changes over time, we can describe the evolution of the path. This integral is called the action functional, which takes in another function as an input and outputs a number called the action, a value assigned to each path.
But what does it mean for the action to be stationary?
In single variable calculus, a stationary point is an extremal point and can be found by setting the first derivative to 0. A similar logic applies in variational calculus. Let's think abstractly for a moment. Imagine a graph where the inputs are the paths and the outputs are the assigned action values. Just as we took the first derivative earlier, we can take the functional derivative, which will tell us the rate at which the action changes as the path varies. By finding the input for which the functional derivative is 0, we have found the true path. The Euler-Lagrange equation is a mathematical way to express this as a condition where given a path in which the action is stationary, an arbitrary amount of variation will not change the value of the action in the first order. Through this, we can solve the differential equations to find the equations of motion. However, this is only the surface of what the principle of stationary action is capable of. It provides a valuable way to view the inner workings of the universe, acting as the backbone of modern physics.